When we talk about the shift theory, if I shift in time domain, in the Laplace domain, we have exponential. Okay? Then, if I times the t, every time in the time domain, if I times t, in the Laplace domain, I'll take the derivative. If I times twice, then I take the derivative twice. Okay? Every time when I times a t in the time domain, then I will have a derivative. Okay? So, let's see this example. If I times the t, I will expect in the Laplace domain, I will have a derivative of that y. So if I want to use the Laplace transform to find the solution, so by the Laplace transform, so I take t y double prime and the second term 4t minus 2 y prime. We separate that. So here you can see that I have Laplace transform of, I can take 4 outside. 4 Laplace transform of t y prime. And then minus 2 Laplace transform y prime. And minus 4. When I take, well, here I just put Laplace transform y equals 0. So first, you'll see the Laplace transform of t y double prime. Again, I times t in the time domain, then I will expect the derivative in Laplace domain. Here it is minus 1 d over ds y double prime. And since I just times t, so here is minus 1 to the, well, my power is 1. So I have minus d over ds s squared y of s minus s y of 0 minus y prime of 0. And y of 0 is 1. Then you have minus 2 sy minus s squared y prime plus 1. And then let's see the second term, ty prime. The Laplace transform of ty prime, I only times 1 t. So here I have minus 1, again to the 1. d over ds Laplace transform y prime. That gives you s y of s minus y of 0 minus s y prime minus y. And the Laplace transform of y prime, that's sy minus y at time 0. So sy minus 1. Therefore, I can change all the original differential equation into the Laplace form. So you'll get the differential equation in the Laplace domain, which is y prime plus 4s plus 8 divided by s times s plus 4 times y. All right. And then we have the differential equation in Laplace domain. And this is what type of this differential equation? Exact, separate, linear, or others, or Riccardi, Bernoulli? And how about its order? First order, second order, third order? Anyone? Yeah. So what kind? First order and linear. Yes. That's linear. First order differential equation. Then your work, finally you will find the y. So you can take the inverse Laplace transform. Okay, check the table. Then you'll get the solution back to the time domain. And your k is c over 32. Okay. And here's a note. You see that our solution, I still have a constant k because we don't have the initial condition of y prime. So we don't have a unique solution. All right. Any questions for this one? So that's all for the Laplace transform. Remember that why do we need the Laplace transform? Because we try to find another way to find a solution. And when you use the Laplace transform, we can we can convert some types of the differential equation into the algebra problems. Okay, and that'll be easy to solve. Next, we are going to talk about the series solution. This is another way to find the solution of the differential equation. And why do we need the series solution? Because sometimes we cannot find the closed form solution. First, what is the closed form solution? So the closed form means a finite sum of arithmetic combination of the elementary functions. These elementary functions or the closed form functions is like polynomials, exponentials, or like a sine functions or cosine function. For example, for the closed form, since we have a closed form solution, then we know how to draw it, and also easier to, well, most of the time easier to draw the solution. For example, if I have this differential equation with the initial condition, then we know that the solution is 1/2 times 1 plus 5 times e to the minus 2x. Okay, this is the closed form because all the elements here are the elementary functions. This is the exponential, then we know that easier to plot. But in this case, we can also find the solution, and here is the solution. E to the x, and then we have integration and apparently this is not the closed form. This solution is not in closed form. And then since it is not in closed form, can you imagine this solution? How does this solution look like? For this one, I have exponential. I know that, and also it's exponential to the minus something, so it will decay. But this one, I have integration here inside, and there's no specific term to express that. So first, it'll be difficult to graph. And then second, we need to compute the numerical values. Okay, we need to plug in each x to get the y. So compute numerical values we cannot just draw the solution right away to other people, to show to other people. So then compute the numerical values, and then we'll probably need a table. When x, here's x and y, when x equals 1, x equals 1.5, 2, 2.5, etc. Then my y, the value of y. So in this case, we need the power series solution. Okay. So what is the power series solution? First, let's see, we should know what analytic function is. So analytic function is a function that can be represented by the Tayer series. And also, analytic function will converge in some interval about a point, say x naught. But here we have a Tayer series. What is a Tayer series? Tayer series, that's f of x equals the summation this is a Tayer series. And we will deal with this later in detail. Okay, so back to this equation. If we say that the Tayer series expansion about 0, because my initial condition is at 0, so the Tayer series expansion about 0 is that means here x naught becomes 0. Okay. So yx should be sigma from n to 0, n from 0 to infinity, 1 over n factorial y of n at 0. Times x to the n. Oh, I want to have n here. Okay, so here we will take the derivative and put 0 in. We can expand this when n equals 0. 0 factorial is 1. So we have y0 plus y prime of 0 when n equals 1. I have x. When n equals 2, that'll be 1 over 2 factorial y double prime 0 times x squared, and so on. The next term will be 1 over 3 factorial y triple prime of 0 times x cubed. You know what factorial is, right? 5 factorial means 4 times 4 times 3 times 2 times 1. Okay. And you can see that this is our solution. And our solution is determined by those coefficients. We need to find the coefficient for this. So the solution is determined by the coefficient. So how do we find the coefficient? First, we know that the initial condition y of 0 is 4. So this is 4. Okay, and we can also plug in 0. X equals 0. So when x equals 0, bring this back to the original differential equation. I have y prime of 0 plus e to the 0 is 1, and y of 0 equals x squared, x 0, so x squared is still 0. Then you get your y prime will be minus y of 0, which is minus 4. So looks like I get another initial condition. Y prime of 0 is -4 here. And then next we need to find y double prime of 0. To find y double prime of 0, then we need to take the derivative of when I take the derivative of the original differential equation, then we get y double prime plus e to the xy prime plus e to the xy equals 2x. Here we can write y prime plus e to the xy equals x squared. Then we can set x equals 0 because we have the information for y of 0 and y prime of 0. So this is 4, this is -4. Then your y prime of 0, y double prime of 0 is 0. Then this term is 0. This term is -4. And this term is 4. And then next, we need to find the coefficient of y triple prime of 0. So I need to take the derivative of this equation. If I take the derivative, then we'll get y triple prime plus e to the x y double prime plus 2e to the x y prime plus e to the xy equals 2. And again, then you can set x equals 0. You have y triple prime of 0 plus y double prime of 0 plus 2y prime of 0 and also plus y of 0. That should be equal to 2. Then you get y triple prime of 0 is 6. So this term is 6. And then if you want to get more, then you take the derivative again. So if you take the derivative of y triple prime plus e to the x y double prime plus 2ex y prime plus e to the x y equals 2, then you get the derivative of the fourth order. And then you'll get y of 0 at the fourth order, that will be 2. So overall, you can still continue, but the solution is in the following form. Y of 0 plus y prime of 0x plus 1/2 y double prime of 0 x squared and then so this becomes 4 minus 4x plus x cubed plus 1 over 12 x to the fourth, and so on. That is your solution. And we call this, especially the Taylor series about 0, that will be Maclaurin series. So we call this is Maclaurin series. Let's have a note here. So Maclaurin series is a Taylor series about 0. Only about 0, that's called Maclaurin series. Otherwise, it is just the Taylor series about 1, Taylor series about minus 2, Taylor series about a point. Okay? Any questions for that? Right. If you don't have any questions, then let's see another example. Because so far, you can see that our initial condition is at 0. But this case, the initial condition is at pi. So since it is at pi, then we will try to find the Taylor series about pi rather than 0. As you can see that we want to determine those coefficients, and if you still want to find the Taylor series about 0, then we cannot use the initial condition. So that's why we need a Taylor series about pi. Okay. So how do we write the Taylor series about pi? So that's the summation n from 0 to infinity. 1 over n factorial. Nth derivative at pi. And x minus pi to the n. You will have y over pi. When n equals 1, you have y prime of pi x minus pi. When n equals 2, we have 1 over 2 factorial y double prime of pi x minus pi square. And let's write one more term. 1 over, when n equals 3, 1 over 3 factorial y triple derivative of pi times x minus pi cube, and so on. Now we need to use the initial condition. So since y of pi equals minus 3, okay, we'll bring this to the original equation. Y prime of pi plus sine pi times y of pi, that equals 1 minus pi. So you get 1 of 1, y prime of pi will be 1 minus pi. So now we found y prime. Next we need to find y double prime, right? How do we find the y double prime? Take the derivative of your original differential equation. So take differentiation. Then we have y prom sine becomes cosine, cosine y, and then sine y prom equals -1. Y double prom plus cosine x y plus sine x y prom, that's -1. Then put the pi here. So y double prom of pi plus cosine pi y of pi sine pi y prom of pi. That's -1. Then you get y double prom of pi minus y of pi equals -1. Then y double prom of pi will be -4. We found y double prom of pi. Alright. Then to find y triple prom of pi, take the derivative of this equation. Then you'll get y triple prom cosine xy, they'll have minus sine times y and cosine x y prom. And similar for here, and the right hand side will be 0. You have y triple prom minus sine xy plus 2 cosine x y prom plus sine x y double prom. That'll be 0. Then you get y triple prom of pi minus 2 times 1 minus pi equals 0. Alright. Then y over x, you have the solution -3 plus 1 minus pi x minus pi, because we are taking the Tayer series about pi. So every time you will see the term x minus pi squared, and x minus pi cube and fourth and so on. So minus 4 divided by 2 factorial x minus pi squared 2 1 minus pi divided by 3 factorial x minus pi cube. So this is the Tayer series. Expansion about pi. Any questions? So far we just see this example of the first order differential equation. Let's see the second order. Using the same idea for the second order differential equation. This is my equation with initial conditions. And seems you need to, well, the question may be asked that how do I know what kind of Tayer series that I need to expand, depending on your initial conditions. See, here's a 0. So I need to get the Taylor series about 0. Okay. And then you may ask that why do I need to use a series solution? Because you use the regular techniques or the techniques we just learned in chapter 1 in the previous topic, and you may find the solution is not in closed form. You may have the integration or something else. It is not straightforward to imagine that solution. Then you may try the series solution. So first, I would like to write the solution in a Taylor series form about 0. That will be y of 0 plus y prime of 0 times x plus 1 over 2 factorial y double prime of 0 x squared plus 1 over 3 factorial y triple prime of 0 x cubed, and so on. From the initial condition at x equals 0, we have y double prime of 0, which means that, we bring this back to the differential equation. Y double prime of 0 minus x is 0, so nothing. E to 0 to be 1, so plus y of 0 equals 4. Then you get y double prime of 0, that should be 3. Because y of 0 is 1, so we get y double prime. This is 3. Then to get the next term, or get next terms, for those coefficients, what should we do? Taking the differentiation. So taking differentiation, we have y triple prime minus y prime minus x y double prime plus e to the xy plus e to the x y prime. That's 0. Okay, here, take the derivative. First term y triple prime, second term chain rules. So we have y prime and x y double prime. E to the xy, also chain rule. Then you set x equals 0. So y triple prime of 0 minus 4 minus plus 1 plus 4 equals 0. Then you find y triple prime of 0, that's 0, that's minus 1. So the Taylor series this solution about 0. All right. Any questions about so far about the series solution? Right now, we just find the Taylor series, and according to your initial conditions, we'll have the Taylor series about the point you have, and then you try to find the coefficients, and those coefficients are the point that you try to expand. Those are your coefficients we're going to find. Next, let's see another example that we have initial conditions, but now it's not the specific numbers, it's just the constants a and b. And when we plug in 0 to the original equation, we have y double prime of 0 plus cosine 0 y prime plus 4 times y of 0 is minus 1. So y double prime of 0 plus b plus 4a is minus 1. Y of 0 is a, right? Cosine 0 is what? Cosine 0 is 1. So here is 1. Y prime of, here we should put y prime of 0. Okay, y prime of 0 is a. Y prime of 0 is b, so that's why we have b. So we get y prime of 0. Okay, y double prime of 0. So y double prime of 0 will be minus 1 minus b minus 4a. Then we take the derivatives of the original differential equation. We have y triple prime, and here chain rule, cosine becomes minus sine y prime, and the cosine y double prime. Here we have for y prime that be equal to 2 minus sine x y prime plus cosine x y double prime, and plus 4y prime equals 2. Again, that we set x equals 0 because we have the initial conditions at 0. Then we can plug in this information to our new differential equation. Y triple prime of 0 minus 1 minus b minus 4a, because here cosine 0 is 1, and for y prime that will be plus 4b equals 2. Oh, sine 0 is 0, so we don't have this term. You have y triple prime of 0 is 3 minus 3b plus 4a. Then the series solution expansion. About 0. Be y of 0 plus y prime of 0 x, and then 1/2 factorial y double prime of 0 x squared 1/3 factorial and y triple prime of 0 plus times x cubed. You have a plus bx. Here's minus 1/2 times b minus 2a x squared. One half minus 1/2 b plus 2/3 a x cubed. Alright, any questions for this example? So far we just have seen some examples and with the initial condition at 0 or even at pi. If it is not at 0 or pi, like here, I have initial conditions at 1. We can still do the same thing, okay, and set x equals 1 and find the coefficients. But we can also change variables. Try to make this initial conditions at 0. So since it is at 1, then we can shift it back to 0, which means when t equals x minus 1, then x equals 1 plus t. So let's see, this capital Y will be the lowercase y 1 plus t. Then your y prime will be dy over dx and dx over dt. That's chain rule. We have y prime of x. And then y double prime will be lowercase y double prime of x. So we change the original equation into this capital Y function, y double prime plus y 1 plus y t, y of t, because now your x becomes 1 plus t. That's 4. And then of course our initial condition will be y of 0 and y prime of 0. So we can use the, well, in this case you can use what you have already learned to find that, right? I think that's easier. But if you want to use series solution, then we can also find the Taylor series expansion about 0 now. So you will get the solution. Remember that later on you need to bring it back to the x, y of x. That will be 2 plus t becomes x minus 1. T becomes x minus 1. Okay, so that is another way to to express the series solution. You can do the same thing as we did when we try to find the Taylor series about pi. So now you can find the Taylor series about 1. Do the same thing. Or you change the variable first. Once you change the variable first, then you get your initial conditions at 0. Because like sometimes when you find the Taylor series about 0, that's easier. Okay. Any questions for this? Then later on we will talk about the power series solutions with recurrence relations. Before we talk about the recurrence relations, first let's have a review. I have a power series in x minus a. That is the infinite series. So I have this form. It's the power series about a. Okay. So I have a coefficient and x minus a to the n. So if I expand this summation, we have a naught a1 times x minus a. When n equals 2, I have a2 times x minus a squared. So this is called the power series centered at a. If it is 0, then it's just that power series centered at 0. But when we express this series, we want to know if this series convergent or divergent. If it is divergent, then if it is divergent, then we probably cannot use that equation to do something else later, right? We hope that the series is convergent. But how do we know that it is convergent? So we say this series is convergent if this Sn converges. And what is this Sn? This Sn is a sequence of partial sum. So the Sn, well, we do this power series, you see the summation is from 0 to infinity. But for the Sn, we have the summation n from 0 to capital N, not infinity. Okay. And then with that, the capital N goes to infinity. So if this summation, finite summation or partial sum converges, then our power series is convergent. Okay. We will see some examples later, but you just need to know that if this series is convergent, then I have a partial sum. This partial sum when n goes to 0, well, when n goes to infinity, this is also converges. This is also convergent. Okay. Yeah, we will see some examples in a minute. And then, since we talk about the convergence, then we need to know what is the radius of convergence. The radius r. Here we have a power series centered at A. And this will be A plus R. Here will be A minus R. And then, So first, if I have parentheses on both sides, we say that the series diverges at both sides, both endpoints. If I have a bracket on both sides, then the series converges at both endpoints. If I have half and half, well, the parentheses on the left hand side and brackets on the right hand side, then the series converges at the right endpoint. But diverges at left endpoint. If we switch, okay, brackets on the left hand side, parentheses on the right hand side, then the series diverges at the right endpoint. And converges at left endpoint. So next, how do we know this series converges or diverges? We have a ratio test. So here's the ratio test. We say that this series converges at x equals a or diverges at x equals a. Well, first, converges at x equals a if the next term, x minus a to the n plus 1, divided by the current term, an x minus a to the n. This absolute value, and then take n goes to infinity. If this is less than 1, then this series converges. If this limit is greater than 1, there'll be that is divergent. Inconclusive if this limit is equals 1. Okay, let's see this example. Is this series convergent or divergent? Using the ratio test. So the ratio test, this is our term, right? We need the next term, n plus 1 divided by the current term. So the next term will be x minus 3 n plus 1 divided by 2 to the n plus 1 times n plus 1. And then the current term x minus 3 to the n divided by 2 to the n times n. Take the absolute value and then take the limit that n goes to infinity and see. First, we can rearrange that and cancel something in common. Okay, so x minus 3 to the n plus 1 divided by x minus 3 to the n. Then we have x minus 3. So x minus 3, I put that outside because there's no n here. Then the limit n goes to infinity. This divided by this, there'll be 2 to the n times n divided by 2 to the n times 2. Right? No. 2 to the n times n. Here, 2 to the n times 2 times n plus 1. Okay, here. So we can cancel this. And that's the rest. N divided by 2 times n plus 1. And when n goes to infinity, this goes to 1/2. Alright. When n goes to infinity, you use L'Hopital's rule. You take the derivative on both sides. So there'll be 1 and here will be 2. So this becomes 1/2. 1/2 absolute value at x minus 3. So this series converges for 1/2 x minus 3. This should be less than 1. So we have x is between 1 and 5 and the radius is 2. You can see those are the endpoints. Okay, when x equals 5, this summation is x minus 3 to the n divided by 2 to the n times n. When x equals 5, there will be 2 to the n divided by 2 to the n times n. We have one over n. This diverge. When n equals 1, or when x equals 1, this summation will be minus 2 to the n. 2 to the n times n. Here we have minus 1 to the n divided by n. And in this case, this converges. Alright. Now, so far we have this background knowledge. Then we can talk about the power series. Okay, and we will use the power series as our solution for the differential equation. And for the differential equation, if we have this power series, then our goal is to find those coefficients. Right? So for the power series, we say that my y is, suppose the y is this summation. Okay. And then we will bring this back to our differential equation to find the coefficients. So we need to know what is the y prime and y double prime. So when you take the derivative with respect to x, that's y prime. Then here this is constant. So this one, chain rule, I have n times an, and then take the derivative here. So I have n minus 1. And here you can see that I will do the n from 1 to infinity rather than 0. Because if you put 0, it's still 0. I have n here. Alright, 0 will be redundant. So my series, my sum is from 1 to infinity. Then I take the derivative of this y prime. For this y prime, when I take the derivative, I have n times n minus 1, and the term, the exponent, becomes n minus 2. And of course, my n is from 2 to infinity rather than 0 or 1. Because if you put 0, here, there'll be all 0. If you put 1 here, it is 0, so it's still 0. It is not necessary to put 0 here. So the term should be from 2 to infinity. Okay. Then we use this concept to find the use the power series solution about 0 to find the solution according to this differential equation. So we know y of x is, this is our power series. And the good thing is that here, a solution about 0, so x naught is 0. Okay. Y double prime, we don't have y prime. Okay, so good. Y double prime, we have n minus 1 an x to the n minus 2. N will be from 2 to infinity plus x squared y. So x squared y. Y is this anx to the n. And times x squared. So n plus 2. That equals 0. Because now x naught is 0. Okay, so this is your x. This is your y. Times x squared. So that's why we have n plus 2. And now how do we solve this equation? We have a different term, different power. So the goal is that we try to make it as a same power so we can compare the coefficients. So we try to get the same power. Then first, for this, the first term, we have, well, I have n minus 2 and n plus 2. So it's better that we choose the middle of that, we choose the middle of their, well, we choose the average of that. So here's n minus 2, this is n plus 1. We probably choose n x to the n. Okay, we change n minus 2 to x to the n. And n plus 2 becomes xn. So we change the variables. n plus 2 becomes n. n minus 2 becomes n. This you will get x to the n. So x minus 2 becomes n. So n becomes what? n plus 2. We're changing variables. Okay. So you can see that the difference is still 2. A m plus 2. So that means m becomes m plus 2. M becomes m plus 2. So you have m plus 2 times m plus 1 and the n is from 0 to infinity. Right, because this n becomes n plus 2 equals 2. So n is from 0 to infinity. Okay? The second term. For the second term, I need x to the n. n plus 2 becomes n. So n becomes n minus 2. Okay? So n becomes n minus 2. So my summation is from 2 to infinity. That should be 0. And you can see that I have the same order. Here I get the same order. So get the same power. So next step, I have the same power. I can combine this summation. But my summation is a little bit different. This is from 0 to infinity. Here is from 2 to infinity. So I also need to rearrange that. We will, since it is from, the summation is from 2 to infinity. So I also want this summation from 2 to infinity. Then I have 2 terms extra when n equals 0 and n equals 1. So that will be 2 when n equals 0. That will be 2 times 1 times a2 x naught. When n equals 1, I have a 3 times 2 times a3 x. So this term is n from 0 and 1. And then we can have the summation n from 2 to infinity. So I combine the red and green. I have n plus 2 times n plus 1 times a to the n plus 2. And the other coefficient is a n minus 2. That is x to the n. This should be 0. Alright, so this equation should be 0 unless this is 0 and this term is also, so this should be also equal to 0. For the purple one, we have a2 equals 0 and a3 is 0. So we found the coefficients a2 and a3. Now when n is 2, 3, 4, 5, this term, we have m plus 2 times m plus 1 a m plus 2 plus a m minus 2. This coefficient should be 0. Then we have n a m plus 2. that'll be minus 1, n plus 2, n plus 1, and here n minus 2. This n is from 2 to infinity. Then you can see that when n equals 2, I have the coefficient a4. a4 is minus 1 divided by 4 times 3 a naught. And a5, that'll be minus 1 divided by 5 times 4, a1. And we know that this is minus 1 over 20 a1. And a6 will be minus 1 over 30 a2. And then we know a2 is 0, so a6 is 0. Next coefficient, a7, be minus 1 over 42 a3. And a3 is also 0. And how about a8? a8, then we know this is 12 times 56 a naught. So the final answer should be a naught plus a1x minus 1 over 12 a naught x to the 4th minus 1 over 20 a1 times x to the 5 and so on. So that is the recursive term. Any questions for this one? So for the series analysis, or you try to find a power series solution, there's no new techniques. It is just a tedious work. Okay, every time later on next week you'll see that a lot of cases that how do we deal with those terms, those powers. We try to make the same power, and then we have since we try to find the same power, we will have additional term. And how do we write the additional term correctly? And then also the recursive term for the coefficients. Those are the main entry. Okay.